Welcome back. We are looking at solving absolute inequalities analytically. And this time we're going to look at solving with the AND case. And how we can tell it's going to be an AND case, you will see that once the absolute value is isolated, you have a less than or equal to a constant. And the main thing at first is trying to understand whether or not that constant is positive or negative. That will clue you into whether or not you're going to have special cases. So let's start off with a nice straightforward case. We're looking at solving analytically this problem. And we look at the fact that we have less than or equal to 12. So that's how we know we have the AND case. So sometimes I write that to remind myself. And the other thing I want to point out, I want you to notice that the number, the constant, it's a positive number. And that kind of clues you into, okay, it's going to be a pretty straightforward case. So if you've done a lot of these, you probably have the pattern in mind, but even if you don't, we have different ways to look at. So what I like to do, there's more than one way. I'll show you both ways and you can choose what you'd like. Always, before we do anything, always make sure we isolate the absolute value first. If you don't do this, you end up getting incorrect answers. So always do this before we do anything. And when you isolate the absolute value first, that means we're isolating the bars. So we would subtract 7 from both sides. Restart. Welcome back. We're going to be looking at solving absolute inequalities analytically. And we're going to go over a few examples to help you see the difference between regular straightforward case and maybe a special case. So the first thing I always want to understand is how do I know it's going to be an AND case? I kind of have a nice sample here where if you see the absolute value bars isolated and you see a less than symbol, then we have an idea that we're going to have an AND case. So before we start with example 10, I know you're probably guessing, oh yes, it is going to be an AND case. You are correct. But before I even judge anything, the first thing I always want to do is make sure you isolate the absolute value bars first. So don't do anything until those absolute value bars are isolated. And what I mean by that is if we're looking at absolute value of 2x plus 1 plus 7 less than or equal to 12, we're going to subtract 7 from both sides. And so we will end up with an equivalent absolute value inequality. Absolute value of 2x plus 1 is less than or equal to 5. And so now we're in a form that we're a little more confident with. Before I try to split up into two cases, I'm going to look at the fact that this number I see right here, notice that it's positive. And when it's a positive number, there's going to be a nice straightforward case. We don't have to think too hard. Moving on from there, generally what you will see me do, there's many different methods. I'll kind of go through both for you. My favorite way is I like to be consistent each time. So whether it's an AND case or an OR case, I like to discover the answer by graphing these problems. So what I will do for myself is I will split up the absolute value inequality into two cases. Case 1 being we drop the bars and keep everything else the same. Always have this connector word, that's the AND case. And the second case, case 2, absolute values generally have 2 cases. We do this dropping the bars, reverse the direction of the inequality symbol, and take the opposite of your constant. So it was +5, it's now -5. Now, if we go through and solve each linear inequality, isolating the variables, I would subtract 1 from both sides. I have 2x is less than or equal to 4. Divide by 2, divide by 2. I have x is less than or equal to 2. Same idea on the other case, subtract 1 on each side. 2x greater than or equal to -6, divide by 2, divide by 2. X greater than or equal to -3. Don't forget your link word. We have an AND going on. Now, this is the informal set notation of your inequality, but a lot of times you can describe it a lot better, a lot more succinct. So in order to find the actual solution, what I like to do is I like to graph both solutions on a number line. And so I have my number line. And when I'm looking at graphing each solution, I will color code it a little bit. I'll still do one in blue. So I'll do the x is less than or equal to 2. Let's make sure before we start, I have blue and green going on. We can plot the boundary points in relation to each other. So I should have -3 is on the left of +2. So they don't have to be to scale, but as long as you know which one is on the left, which one's on the right. So graphing, x is less than or equal to 2. That would mean that I would be shading to numbers that are smaller than 2. So I'm going to be shading to the left of 2. And less than or equal to means I have a bracket on the 2, facing always the way you're shading. Now, x is greater than or equal to -3 means you would be shading to numbers that are bigger than -3. And you'll have a bracket opening up to where you shade because you have the greater than or equal to. Now, this is an idea of how to get your graph. You need to have your final solution or your final graph. And this is what's important of why we should know the link word. The final graph, still number line. What we're dealing with is if we do have the AND case, AND means take the intersection of the 2 graphs that you have just written down, or drawn, I should say. So if you remember, AND means take intersection. And whenever I take the intersection, what have I colored twice? And so if I'm looking at it, I can see right away, I've colored this region twice. That is the intersection. So that is going to be my formal solution. So there's a better way to write this. So if I can do this for myself, I will. I will start off with -3, shading all the way to 2. There's my final graph. And now if you have it much more compact in understanding what the solution is, you can now write your actual solution. Sometimes people ask for it in interval notation. Sometimes we ask for it in set notation. If you look at directions, it didn't specify. So we have freedom here. I will go with interval notation. It's one of my favorites. So if I'm trying to describe what my final graph looks like, I'm going to be just saying it's all the numbers in between -3 and 2. It's very nice. I kind of just copy the brackets. And we have solved an AND case analytically. Now, what I'd like to play with is there is a straightforward, like a procedure that you can take without having to draw the graphs. So I'm going to do this one more time with you. This is good if you have an idea of all the special cases. I always prefer my first technique first because you really can tell what the solution is based on what your graph is. So you don't always have to memorize every special little thing. But for those of you that are excited about this, let me write this down one more time. 2x plus 1 plus 7 less than or equal to 12. So one more method. First things first, we always isolate the absolute value. So that has never changed. It's always the case. So I should have absolute value of 2x plus 1 less than or equal to 5. And that hasn't changed. Number one, this is why it's important. Note that this is a positive number. And when this is the case, and you know you're dealing with and, you can rewrite this as a three-part inequality. So maybe you've seen it this way before, and that's cool. I'll walk you through it just in case. What do we mean by three-part inequality is it takes the expression that's inside the bars, 2x plus 1, and it places that expression in between both cases of this positive number. So if you're looking at 5, you would have the 5, positive 5, and then the other case of the 5 would be negative 5. So it's kind of another technique. And then if you're going to solve this three-part inequality, what happens is you still have to go through and isolate your x in the center. So it's kind of like you don't have to do things twice. You're solving all in one. So if that is the case, we subtract 1 from each of the parts. 3 parts, not 2 parts. So we should get negative 6 is less than or equal to 2x is less than or equal to 4. Then we divide every part by 2. And we end up getting negative 3 less than or equal to x less than or equal to 2. And it kind of gives you the nice set notation. You don't really need a graph when you have this. So you could say in set notation, it's all numbers x such that negative 3 less than or equal to x less than or equal to 2. Or if you like interval notation, we would have negative 3 to 2. And so notice, it's the same thing. And so people like this one because it's a little less graphy, but it only works if you have a positive number after you've isolated the absolute value. So in the next example, you'll see that, you can't quite do that. It causes some confusion. So this is why I still stick with the graphing so I could understand just a little bit of why I'm taking the solution that I'm taking. So hope this helps. See you in the next example.